Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder a component in Vero board. Use a soldering iron and sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated Vero board for your prototyping. In our previous session, we have learned that how to display the digital data on a multiplex 7-segment display, and here we can find a counter is running on multiplex 7-segment display, and we have developed this project in our previous session. In this session, we will learn that how to interface analog signal with embedded system. Here we can see we have connected two variable resistors, that is VR1 and VR2, and the labels are analog 0 and analog 1. And these analog voltages are coming at pin number 2 and pin number 3 of the microcontroller, that is analog 0 and analog 1 input of this microcontroller. This microcontroller can read up to 8 analog inputs. Here we can find analog 0, analog 1, analog 2, analog 3, and here we have analog 4, analog 5, analog 6 and analog 7. So we have connected two variable resistors on analog 0 and analog 1. And these variable resistors are connected on port RA0 and RA1. First, we understand that how to interface analog parameters with microcontroller or any embedded system. As we know that the world in which we are living, most of the parameters are analog parameters, like temperature of the environment. To control the temperature of a room, we use air conditioner and we use heaters. Almost all modern days air conditioners, they have electronic controls with them. The electronic control reads the temperature of the room with the help of some sensor. It could be thermocouple, it could be PT100 or some other sensor like LM35. And to regulate the temperature of the room, electronic control cards control the status of compressor. And to regulate the temperature of the room in case of heating, electronic control cards control the status of solenoids. To control the supply of the gas to the heater, in some projects it is required to control the speed of a motor. To control the speed of a motor, we require a drive. Here we have a DC drive based on pulse width modulation, that is PWM controlled DC drive. And to get the speed feedback of a motor, we require a tacho generator. Or there could be an encoder. And we require a processor card to control the speed of the motor with the help of drive and with the help of feedback device, that could be tacho generator or encoder. In industrial control system, different parameters are required to be regulated, like pressure, flow, humidity, and different types of parameters are required to be controlled and monitored with the help of embedded systems. There are two possibilities to get the data from these devices. That could be a serial based or analog. So in this session we will learn that how to interface the analog parameters with microcontroller. In some projects it is required to monitor the voltages, that is 220 volt or 110 volt, and to monitor the load current which is connected with the power supply. Here we can find a digital meter which can display the status of voltage and current. To monitor the voltages of a battery, different types of voltmeters are available in the market. All these devices which can read the analog voltages and can process the data in digital format, they use ADC. ADC is a device which can convert the analog voltages into digital form. What is the significance of converting any signal into 0 to 5 volt? As we have interface in our prototype system, there could be different types of analog parameters like temperature, like voltages, current, humidity, pressure, flow, and so on. Say for example, if you would like to read the temperature of a room, so we'll use the temperature sensor, that is LM35. LM35 is a temperature sensor. It can convert the temperature directly into voltages, and it can read from 0 degrees centigrade to 150 degrees centigrade, and its output voltages are 10 millivolts, per degree centigrade. We can find different parameters of LM35 sensor in the datasheet. Here we can find the datasheet of LM35 precision centigrade temperature sensor, and we can see it's calibrated directly in Celsius centigrade, linear plus 10 mV per degree centigrade scale factor, and we can use this sensor to read the temperature from -55 degrees centigrade to 150 degrees centigrade range. Basically, this sensor is designed to read the temperature from 2 degrees centigrade to 150 degrees centigrade. But to read the -55 degrees centigrade, we have to add another resistor with minus supply. And here we can see the wide range of power supply, that is from 4 volt to 30 volt. Here we can see the power supply is 4 volt to 20 volt and output is 0 mV plus 10 mV per degree centigrade. Basic centigrade temperature sensor, that is from 2 degrees centigrade to 150 degrees centigrade. And to read the temperature from -55 degrees centigrade to 150 degrees centigrade, we have to add resistor R1, and the value of R1 is minus voltage supply divided by 50 microampere. Vout is 1500 mV, that is 1.5 volt at 150 degrees centigrade, and Vout is 250 mV, that is 0.25 volt at 25 degrees centigrade, and Vout will be -550 mV, that is -0.55 volt at -55 degrees centigrade. And here we can find 3-pin TO92 package. The bottom view, pin number 1 is V positive, pin number 2 is output, and pin number 3 is ground. Here we can see TO92 package. And pin number 1 is from the left side, which is power supply voltage. Pin number 2 is V out, output voltages, corresponds to the temperature. Pin number 3 is ground. So in this case, we can develop a circuit like this. Here we have LM35. Here we have pin number 1, that is V positive, and we have ground, that is pin number 3, and here we have the output pin, that is pin number 2, LM35, and here we'll place a capacitor. That is 4.7 microfarad, 16 volt, and here we'll get maximum voltages, that is 1.5 volt at 150 degrees centigrade. So how to interface these voltages with microcontroller? As you know that the full scale conversion of PIC microcontroller, that is PIC 16F877A, is from 0 to 5 volt, and PIC 16F877A microcontroller can convert these voltages from 0 to 5 volt into two different resolutions, that is 8-bit and 10-bit. So if we use 8-bit conversion, then the 5 volts will correspond to 5 volts will be equals to 255 as digital value, and if we'll use 10-bit digital conversion, then 5 volts will correspond to 1023 as digital conversion. So how to interface these 1.5 volt to the microcontroller? We'll use an amplifier circuit to amplify these voltages up to 5 volt, and we'll use an op-amp circuit. Here we have amplified these voltages to get the benefit of full range. So what will be the value of these resistors? As we know that this amplifier configuration is non-inverting amplifier, and we know that the gain of non-inverting amplifier can be written as V out equals to V in 1 plus RF over R in. So if R in is 10K, then we can calculate the value of RF. So we'll write 5 volt output, V in is 1.5 volt equals to 1 plus RF over 10K, and we can write 5 by 1.5 minus 1 multiplied by 10K equals to RF, which is equals to 23.33K. As we know that 23.33K is not a standard resistor, so we can add a variable resistor to the fixed resistor to make this value. We can use a resistor of 22K with a variable resistor of 5K to get this value, that is 23.33K. Now we'll wire up these resistors with microcontroller and we'll read the voltages, and we'll also display the voltages on LCD display. Here we have two variable resistors, and these resistors are 5K multi-turn resistors. So we'll place these resistors here on this position, and we'll connect the center pin of these variable resistors with pin number 2 and pin number 3 of this microcontroller. Now we'll solder these resistors in Vero board. First I'll solder only one pin of both these resistors. Now we can check the proper alignment of these variable resistors. Now we'll solder other two pins. Here we have soldered both the variable resistor in Vero board. Now we'll complete the connections for these resistors. Here we have connected end pins of both the resistors together, and I'll apply 5 volts at one end and ground on second end. And here we have the center points of both the resistor, and these points will be connected to pin number 2 and pin number 3 of the microcontroller. Now we'll connect 5 volts at this end of variable resistor, and we'll connect this end of the variable resistors to the ground. Now we'll check the 5 volt and ground connection near to these variable resistors. So here we can find this end of the switch is connected with ground, and from schematic we can see that this end of the resistor is connected with 5 volt. Now we'll apply 5 volts and ground to these variable resistors from these points. Here we have connected ends of the both variable resistors to VCC and ground, that is plus 5 volt and ground. Now we'll connect the center point of the variable resistors, that is viper of the variable resistors, to pin number 2 and 3 of the microcontroller, that is analog 0 and analog 1. For this we'll use wrapping wire. Here we have variable resistor 1 and variable resistor 2. We'll connect the variable resistor 1 to the pin number 2 of the microcontroller and variable resistor 2 with pin number 3 of this microcontroller. Here we have connected the center pins of the variable resistors with pin number 2 and pin number 3 of the microcontroller. Now we'll perform the voltage test on pin number 2 and 3 of the microcontroller. For this, we'll remove the microcontroller from the base. Now we'll energize the prototype and we'll measure the voltages on pin number 2 and 3 of this microcontroller. We will place common probe of the multimeter on center point, that is ground connection, and we'll check pin number 2 of the microcontroller. Here we can check. We have 1.4 volts at pin number 2 of the microcontroller. Now we'll test pin number 3. Here we have 2.72 volt at pin number 3 of the microcontroller. Now we'll vary these voltages with the help of variable resistors. Here we can observe the voltages are changing at pin number 2 of the microcontroller and the value will go up to 5 volts. Here we can check at pin number 2 voltages are 5 volt. Now if we'll move the variable resistor on other side, the voltages will go to the 0 volts. Here we can check minimum voltages are 0 volt at pin number 2. Now I'll perform the same test on pin number 3. We'll move the variable resistor for higher voltages. Here we can see we are getting 5 volts at pin number 3 of the microcontroller. Now I'll move the variable resistor on other side. Here we can check minimum voltage at pin number 3 is 0 volt. So we have adjusted the voltages 0 on pin number 2 and 3 of the microcontroller. We can check on pin number 2, voltages are 0 volt, and on pin number 3, the voltage level is 0. Now we'll insert the microcontroller into the base and we'll read the voltages at pin number 2 and pin number 3 of the microcontroller, that is analog 0 and analog 1 of microcontroller. Here we have inserted the microcontroller into the base. Now we'll start writing a program to read these voltages at pin number 2 and 3 of the microcontroller, and we'll display the detail value on LCD display. So we'll also insert the LCD in header pins. Now our prototype is ready to read the analog voltages coming from variable resistors, and we'll display the raw digital data on this LCD display. We'll also learn that how to read the value of ADC as 8-bit and 10-bit.